In a previous video, we commented that solids and fluids are very different because of the mobility of their particles. We started to look at the physical properties of the fluids. Then we talked about density and other related properties and about the specific heat. Today we'll talk about two other properties, surface tension and viscosity. Let's start with the surface tension. What is it exactly? Well, we can say that it's a tension which develops on the interface of a liquid and a gas, or even between two liquids, caused by the intermolecular cohesion forces. In this way, the external surface of the liquid in contact with the gas, or with the liquid with greater surface tension, in the case of immiscible liquids, tends to contract. Surface tension is represented by a force sigma, which acts by length unit of the interface. Let's see what happens in this water droplet on a horizontal surface like glass or on a surface that also has a thin oil film on it. For a small droplet, its shape is almost perfectly spherical because in this configuration there is the least surface area for a given volume. But as the volume of the droplet grows larger, the shape turns flatter and flatter because of the increasing gravitational effect. But note that it keeps its cohesion. Let's examine the case of this dropper. Note that a droplet is ready to fall. The critical section is this one. The surface tension will fail here, where the perimeter is smallest. The maximum force developed by the surface tension will be sigma times 2 pi r. It can support a droplet of radius r. The weight of the droplet will be equal to gamma times 4 over 3 times pi r to the third. So, at the critical condition, we'll have F1 equals F2, which means sigma times 2 pi r equals gamma times 4 over 3 pi r to the third. Thus, r equals 3 sigma r over 2 gamma to the 1/3. Let's find the general equation for the surface tension. Here is a droplet of a liquid standing over a surface that is not wetted by it. We'll consider this elementary area. Its dimensions are dx and dy. Here is the elementary area shown in perspective and upside down. It has two different radii for its curvature as shown. Here we see a section of the area showing the curvature r1 and length dy, and here a section of the same area showing the curvature r2 and length dx. We can write sin alpha equals dy over 2r1, sin beta equals dx over 2r2. Then we write this expression, which comes to this, and finally P1 minus P2 equals 2 sigma times 1 over r1 plus 1 over r2. In this table, we can find the values of the surface tension for some common fluids in contact with one another at usual temperatures. Capillarity is another interesting problem that we can solve using the surface tension concept. See in this figure that the liquid column is stable in the interior of the transparent tube. The equilibrium height is h. Its weight is rho g pi squared r h. The force that sustains the liquid column is equal to 2 pi r sigma cosine alpha, where sigma is the surface tension, whose value we saw in the table, and alpha is the contact angle. We'll see its value in a table in just a while. The liquid weight equals the force, so the height will be equal to 2 sigma cosine alpha over rho gr, or h equals 2 sigma cosine alpha over gamma r. Here is the table that we talked about, containing the contact angle of some liquids to glass. Note that the smaller the radius, the higher H will be. The most remarkable consequence of capillarity in our activities is the infiltration that can occur in foundations of buildings. Special care must be taken for in this particular item. There are minimum values for the diameters of the devices used for pressure measurement that we'll study moving forward. For example, for mercury manometers, minimum D should be 20 millimeters. And for glass tubes used in piezometers, minimum D should be 6.3 millimeters, though some authors recommend that they should be between 9.5 to 12.7 millimeters. Well, here's a controversial matter: cohesion and adhesion. We assume that there are two fundamental tensions between the liquid molecules and the walls of its container, and between the molecules themselves. The first ones we call adhesion, the second ones we call cohesion. When adhesion is greater than cohesion, the liquid will ascend inside the capillary tube. It's the case of water in glass. When cohesion is greater than adhesion, the liquid will descend inside the capillary tube. It's the case of mercury in glass. Now that you're happy with the surface tension explanations, imagine the happiness of these bugs whose lives depend on it. Or the joy of the Jesus Christ lizard who can run over water. Our next topic is viscosity. We can say that viscosity is the natural opposition to fluidity. Liquids with greater viscosity, such as honey and oil, have smaller fluidity and, consequently, greater viscosity. In standard environmental conditions, the viscosity of the liquids decreases with temperature. In opposition to it, the viscosity of the gases increases with temperature. We've explained that in another video. I'll leave the link in the description. The scientist who stated an equation for the viscosity was Newton. Yes, sir, the Sir Isaac Newton. Here we can see a fluid between two parallel solid plates shown in perspective and in transversal cross-section. Here's the fluid between the plates. This one is a fixed plate and this one is a mobile plate. Let's apply a tangential force F on the upper plate. It will move with constant velocity v. See what happens to the fluid. The particle that is near the mobile plate moves with it, and the particle that's near the fixed plate stays with it. We're assuming that there's a linear velocity profile, which means that the velocity variation is proportional to the distance. So we have v over y equals dv over dy. Velocity gradient is the name of this relationship. The relationship F over A equals tau is the shear stress. The relationship shear stress velocity gradient, named mu, is called absolute viscosity or dynamic viscosity. The Newton's law of viscosity states that tau equals mu dv over dy. In this expression, tau is the shear stress, dv over dy is the velocity gradient, and mu is the absolute viscosity or dynamic viscosity. At 20 degrees Celsius, the water absolute viscosity is approximately equal to 10 to minus 3 pascal second. Kinematic viscosity is a measure of a fluid's internal resistance to flow under gravitational forces. Its expression is nu equals mu over rho. At 20 degrees Celsius, water kinematic viscosity is approximately equal to 10 to minus 6 squared meters per second. In this table, we can see the water viscosity variation with the temperature. It varies a lot. And in this table, we can see the air viscosity variation with the temperature. It's a considerable variation. Well, that's enough for today. So far, so good, isn't it? In our next video, we'll see how to apply tensions to fluids. In special, we'll talk about pressure. See you there! Oh, and if you like this video, don't forget to give it a like, comment, share, and subscribe. Hit the bell so you can be notified of my next videos.